Now we will move into the third lecture, that is called the central limit theorem. So this is a very important result in probability, that is central limit theorem, which has the wide application in many real world problems. Therefore, this theorem will be used again and again in many problems. So let me give the central limit theorem first, then I give the proof, then we will go for one or two examples of how to use the central limit theorem in the real world problems. Let me give the theorem first. Even though there are many versions over the central limit theorem, first we will give the easiest version, because it is a introduction to the probability theory and stochastic process course. If the course is advanced probability theory course, then we can go for 2-3 levels of a central limit theorem. So here we will present only the simplest version of the central limit theorem, whereas we will discuss how the complicated version in the central limit theorem after I give the proof of the simplest one. So we will give the simplest version of the central limit theorem. Let omega f capital P be a probability space. Let x1, x2 and so on be a sequence of IAD random variables defined on omega f capital P. Assume that expectation of xi, that is equal to mu, and variance of xi, that is equal to sigma square, which is greater than 0 for I is equal to 1 to exist. That means we make sure that this sequence of random variables are IAD, as well as at least a second order moment exist, and the variance of each random variable is greater than 0. Since I made it IAD random variable, the sigma square is greater than 0 and also the finite quantity. I am defining the new sequence of random variable. I call it as a z suffix n, that is nothing but sum of n random variables minus expectation of these sum of random variables divided by square root of variance of sum of these n random variables. I am defining a sequence of random variable for n is equal to 1, 2 and so on. What the central limit theorem says, then for larger n, Zn approximately standard normal distributed. random variable. Then for larger n, Zn approximately a standard normal distributed random variable. That means the probability of Zn less than or equal to small z approximately minus infinity to z 1 divided by square root of 2 pi e power minus t square by 2 dt. This is valid only for larger n, that is very important, and that too the CDF for the random variable z approximately the integration from minus infinity to z 1 divided by square root of 2 pi e power minus t square by 2 dt. That is nothing but the CDF of standard normal distribution. This is valid as long as xi's are IID random variables defined on a probability space with at least a second order moment exist and the variance is strictly greater than 0, and then making a sum of random variables minus their mean divided by the standard deviation, that is approximately a standard normal distributed random variable for a larger n. Indirectly, whenever you have a normal distribution with the parameters mu and sigma square, by subtracting the mean divided by the standard deviation, that becomes a standard normal distribution. So the same thing we are applying in the Zn. The random variable is a sum of random variable, that's a one random variable for fixed n, minus their mean divided by the standard deviation. That means this transformation is a transformation from normal distribution to the standard normal. That means indirectly when we say Zn approximately a standard normal distributed random variable, indirectly what we are saying, the sum of n random variable approximately a normal distributed random variable with mean expectation of that random variable with the variance of sum of random variable for larger n. That's the meaning of Zn approximately a standard normal distributed random variable. That is equivalent of sum of random variable is approximately a normal distributed random variable with the mean is expectation of a sum of random variable and the variance is variance of sum of random variables. And here the assumptions are very important. It should be IID random variables with the at least a second order moment exist. Now we will go for proof of this theorem. For the proof, we will make the assumption that MGF of each xi's exist, even though for some random variable MGF may not exist. And here we made the assumptions only at least second order moment exist. That does not mean that MGF or moment generating function of each xi's exist. We make the additional assumption of MGF exist, then later we will relax the MGF exist, then we can give the proof of it. So without loss of generality, we assume that MGF of xi's exist for all the random variables because all are IID random variables. With that assumption, we will give the proof. Later we can relax this also. Let us go for finding out the MGF of Zn as a function of t, moment generating function for the random variable Zn as a function of t, that is nothing but expectation of e power sum of random variables 1 to n. Since we made all our IID random variables, their mean is going to be mu n times mu divided by variance of sum of random variables. Each random variable variance is sigma square. Therefore, sum of random variables is n sigma square. Here you need a square root of variance. Therefore, square root of n sigma as a function multiplied by t. So, this quantity is going to be the MGF of the random variable Zn. This is possible as long as the MGF of Xi's exists. Therefore, we made the assumptions MGF exists. That is same as all the constant you can take it out. Therefore, it is going to be exponential of minus n times mu t divided by square root of n sigma multiplied by expectation of e power 1 divided by square root of n sigma, then the summation of x i's 1 is equal I is equal to 1 to n times t. This is same as e power minus square root of n mu t divided by sigma. You can use the expectation of e power summation of x i's t, that is nothing but the all are IID random variable. Therefore, you can go for expectation of e power 1 divided by square root of n sigma for one random variable x1 t. After getting the expectation, you can raise it to the power n, because all are independent as well as identical. That is same as e power minus square root of n mu times t by sigma. This is nothing but a MGF of the random variable x1. Instead of t, you can write t divided by square root of n sigma. Both are on the same. Whether you write MGF of 1 divided by square root of n sigma x1 of t, or MGF of x1, t is replaced by t divided by square root of n sigma, both are one and the same. This power n because of identical. Now we need the expansion of MGF for any random variable, then we can substitute that. We know that MGF of any random variable x can be written as 1 plus mu t plus expectation of x square t square by 2 factorial and so on. Again, you can write expectation of x square as variance of x, suppose variance of x is sigma square, plus mean square. So, one can write expectation of x square as a sigma square plus mu square. I am going to substitute little later. By taking a logarithm of MGF of xt, I can use ln of 1 plus x as x minus x square by 2 plus x cube by 3 and so on, provided mod x is less than 1. I can use this identity for the ln of MGF of x is ln of 1 plus mu t plus expectation of x square t square by 2 factorial and so on. So, I can make it as a ln of 1 plus all the other term, I can make it as the sort of x mu t plus expectation of x square t square by 2 factorial and so on. This I can keep it as a 1 plus x form. So, I have not substituted ln of 1 plus x. Now, I am just writing ln of the whole series as the 1 plus remaining terms as the x. Now, I am going to apply the same logic for the MGF of Zn. That means now ln of MGF of the random variable Zn of t, that is going to be, when you take a logarithm, it becomes a minus square root of n mu t by sigma, then the remaining terms with the power, therefore it becomes n, power n becomes n times ln of 1 plus mu. Here t is replaced by t by square root of n sigma plus expectation of x square is sigma square plus mu square times t square by 2 factorial n sigma square and so on. This is going to be minus square root of n mu t plus divided by sigma plus, now I am going to apply ln of 1 plus x, that is n times, it is x minus x square by 2 plus x cube by 3. So, x is going to be this so the first terms in the x, that is mu t divided by square root of n sigma plus sigma square plus mu square t square divided by n sigma square, 2 factorial is 2. I am not going to write. Other terms of x, I leave it as it is. Whereas now I am going to write minus x square by 2 terms, that is minus 1 by 2 times, in the x square also I am not going to write x square of all the terms, I am going to write the x square of only first term, that is mu square t square by n sigma square. All the other terms I leave it as it is. There is a reason behind that. I am not going to write other terms of x square. Similarly, I am not going to write any terms for the x cubes, only I write 1 by 3, all the other terms as it is. Like that there are some more terms for the expansion of ln of 1 plus x. This is going to be close bracket. The reason is, as n tends to infinity, even though I use the word for larger n, here we are going for as n tends to infinity. The n in the numerator and many terms in the n in the denominator, that cancelled, and all the other terms will be in the form of 1 divided by n. Not only that, this one and this one cancel, whereas the sigma square plus mu square t square, this one with the first term here, that cancels. So, the left out is sigma square t square divided by 2n sigma square, that will be cancelled with n in the numerator. So, you will have only sigma square t square by 2 sigma square also cancels. So, you will left out with t square by 2. Even though we have many more terms, as n tends to infinity, all the other terms will vanish. So, you will have as n tends to infinity, ln of mgf of Zn is going to be t square by 2. All the other term vanishes as n tends to infinity. Now I am taking exponential both side, that means mgf of Zn, that is going to be e power t square by 2. If you recall the moment generating function for the standard distributions, we have discussed for many discrete type random variables. Similarly, we have discussed continuous type random variables MGF. So, if you compare the MGF of this with the MGF of a standard distribution, you can conclude by using the uniqueness theorem of two different MGFs are same for all t, then both the random variables are identically distributed. So, you can conclude Zn is standard normal distribution. So, this is valid for n tends to infinity. That means for a larger n, the Zn approximately a standard normal distribution. That is a proof. In this proof, we have made assumption of MGF exist. Now we can see what could be the proof or how the proof goes when we do not have an assumption of MGF. The similar derivation I can go for characteristic function. So, the characteristic function of Zn of t, that is going to be expectation of e power the whole expression t, where t is replaced by I times t, where I is square root of minus 1. For that I do not need any assumption, because the characteristic function exists for all the random variables. Therefore, the characteristic function for Zn exists. So, I can directly compute the characteristic function of Zn. In this result, wherever the t I have to replace by I times t, that is going to be the derivation of characteristic function via. So, if I do the same derivation, everything goes in the same fashion, because I keep IAD random variables, mean is mu, variance is sigma square, and so on. Therefore, wherever there is a t, it will be replaced by I times t, so that will be cancelled. Wherever there is a t square, that is going to be minus t square, because it is going to be I square t square, I square is minus 1. After you do the simplification till the as n tends to infinity, you will get the answer minus t square by 2 for the ln of characteristic function of Zn. That means the characteristic function of Zn is going to be e power minus t square by 2. That is the result for the characteristic function for standard normal distribution. Then we can conclude also Zn is approximately a standard normal distribution. So, whether we made the assumption MGF or not, the derivation is almost similar way to conclude it is approximately a standard normal distribution. I said I am going to discuss the little higher versions of the central limit theorem. Yes, see the theorem carefully. I have made a IAD random variable. Suppose if it is not identically distributed, then you can find what are all the changes. That means if each xi's are not identically distributed, then their mean will be mu i's, variance will be sigma I squares. That means each one may have a different means. Still you can apply the theorem, because Zn is going to be sum of random variable minus their mean. So, whatever the mean mu i's, you add all the mu i's, find out the summation of mu i's, that is going to be the expectation. In this theorem, when they are identical, it becomes n times mu. If they are not identical, then it becomes mu 1 plus mu 2 plus so on mu n. Similarly, the denominator, here it is a square root of n sigma, but if they are not identical, then you will have a sigma 1 square plus sigma 2 square and so on, square root of that. Still the derivation goes, but we cannot apply the power n. We cannot apply the power n the way we have done it here. Because of identical we got power n. So when you go for derivation for non-identical distributed random variable, you have a individual MGF in the product form. So when you take a logarithm and so on, the expression will be huge. The process of a derivation may be tedious, but still as n tends to infinity, you can conclude the same result. The derivation may be very complicated when they are non-identical distributed. Still we can go for it, the same derivation. One more observation, here we have used the independent random variable in finding the square root of variance of sum of random variables. Since all the random variables are independent, the variance of sum of random variable is nothing but the individual variance summation. If they are not independent, then you have to go for adding the covariance of any two random variables. So since we made the assumptions they are independent random variable, we are finding the individual variance, then we are sum it up, that is going to be the variance of sum of random variables. Otherwise you have to use the covariance of any two random variables. That means we can relax, instead of they are independent random variable, you can make the assumptions all the random variables covariance of any two random variables is 0. That's enough. You don't need a independent assumption. Independent is the strongest assumption comparing to the covariance of any two random variables are going to be 0. Because the covariance of any two random variables 0, that does not imply they are independent. But if two random variables are of some random variables are mutually independent, then the covariance of any two random variables are going to be 0. So here in this theorem I made a strongest condition, therefore this is the simplest version of central limit theorem, whereas we can go for covariance of any two random variables are 0, that's enough to use the central limit theorem. One more observation over the central limit theorem, why this is used in many situations. You see the theorem very carefully, we have not used any distribution for random variables xi's, and we have used only the mean and variance of random variables and assumption of independent, nothing else. Because of that this theorem is used in many real world problems. That means many real world problems, many random variables which we have created, those random variables we may not know the distribution of that. We may not know the distribution of those random variables, but we may know the mean and variance as the numbers. We may know mean and variance of those random variables. Even they are dependent, or the dependency may be very minimal, or we can ignore the dependency, or we can make the usage of those random variables are independent, or in the lighter sense we can use the concept of covariance of those two random variables are 0. With that assumption you can use this theorem. So the big advantage of this theorem is there is no assumption over the distributions, or you don't need the distribution of each xi's, we need only the mean and variance. Therefore we can use this theorem to find out the probability of event using a standard normal distribution by approximating this random variable as a standard normal distribution. That means whatever be the distribution of those random variables, once you sum it up by subtracting their mean divided by the standard deviation, for larger n we can always approximate immaterial of whether it is a discrete type random variable or continuous type random variable, as long as they are independent random variable, that can be approximated with a normal distribution. By normalizing, it can be approximated with a standard normal distribution. Therefore we use this theorem quite a lot in many real world problems. Now let us go for a few examples how one can use the central limit theorem.